Hello and welcome to our next set of statistics notes. We are starting chapter 8. I mentioned in chapter 7 that was an important section. We're getting to the idea of confidence intervals, and we'll use these all the rest of the semester. I could say the exact same thing about chapter 8. Chapter 8 is very important. We're going to get into the basics of hypothesis testing. I will say that maybe chapter 8 is actually a little bit more important than chapter 7, because hypothesis testing is a very, very essential tool for statistics and statisticians. And we are going to use this throughout the rest of the semester. We will be doing hypothesis testing a lot. So this first section of chapter 8 is going to introduce the idea of what hypothesis testing is and how it works. So that's what we're going to be doing in this section. And sections 8.2, 8.3 will actually do some hypothesis testing in certain situations. But this first section is just to introduce the whole idea, go through and talk about what it means. So there's a lot to cover because we want to kind of step by step go through and really explain what is hypothesis testing so you get a good idea of it. So we already mentioned earlier in the semester, talk about claims and how you can kind of test claims. And that is a big thing in statistics, and that's what we'll use hypothesis testing for. We'll look at someone's claim and we'll try and decide if we agree with it. We'll go and collect sample data and we'll test their claim with our sample data. So a hypothesis is a claim about a property of a population. So they'll claim something about the average for all the people in the US, or they'll claim something for the percentage of people in the US. When they look at the whole US, that's the population they're looking at, they're going to make some kind of claim, and then we'll test that claim. So hypothesis is a claim about a population, the whole group. So examples would be that someone says the mean body temperature is 98.6. That's the average temperature for all bodies. Someone says more than 50% of consumers are not comfortable with drone deliveries. Their percentage is more than 50%. That's in a claim about the entire group. Half the group feels a certain way. And the IQ test scores have a standard deviation less than 20. So they're looking at the whole group and they're making a claim about the whole group. Once we have a claim like this, we're going to take it and we're going to translate it into two separate hypotheses. We're going to state both a null and an alternative hypothesis for every claim we deal with. The null hypothesis, so the null, usually we write H0 for null, 0 means null or 0, is a statement that the population parameter equals some claimed value. So the big thing is the null is always a statement of equality. So when they say 98.6 is the body, human body temperature, we turn it into an equal statement like that, that would be like a null hypothesis. A greater than like this, it wouldn't be a null. We'd actually turn it into an equality statement for a null. So null is always going to be a statement of equality. So that the value for the population is equal to their claimed value. So whenever you have a null statement, it's always going to be a statement of equality, that the actual value for the population, the actual percentage or average for the population, matches the value that they're working with. That's going to be your null statement. Your alternative, alternative is going to be your other option. That's why we use the word alternative. Instead of the main option, the null option, we go with the alternative. We either use H1 or HA. So it's not 0, it's 1. It's not 0, it's A. Alternative, A for alternative. So that is going to be a statement that the population value, the value for the population parameter, is different from the null. So this is a statement that the population parameter is different, that's the big word, different from the null. So it's going to be a statement of either like less than, it's not bigger, it's not equal to, it's less than, or it's greater than, or it'll be a statement that's just not equal to. So if I'm talking with population means, if I'm looking at averages, we'll do this for both means and proportions in the future, but if I'm looking at just specifically means, here would be some statements of what you'd see for like a null and alternative. So a null statement would look like this, where you'd say the average for the whole population, the real average for the group, is equal to null, this mean sub 0, which we'll say is our claimed average. So if I go say the average height of high school boys is 5 feet 6, then my claim would be the 5'6" height, and the null hypothesis would state that the average for all high school boys is 5'6". My claim is, accurate. That'd be the null statement. Always a statement of equality. The value is equal. That's the big thing with null. Then the alternative could be any one of these next three. It could be a not equal to statement. because it's just not 5'6". We're not going to specify if it's more or less. We're going to say it's not the same. It's different. It could be a statement of less. So they say, no, it's not equal to 5'6". It's less than 5'6". So that'd be another alternative. And they say it's actually less than. And then the third option would be saying, no, it's not less than 5'6", or not equal to 5'6". It's more than. So you have the third statement would be that the actual average for high school boys is actually more than 5'6", greater than. So those would be, three different options for null, or alternative, sorry, alt. And there's only one option for null. So if you're making a null statement, you should always be using equal. Null statements, null hypothesis, always are a statement of equality. An alternative is always a statement of not equal to. Those are the two things we're always working with. We're always going to work with a null and alternative. Null is going to stay equal, alternative is going to stay not equal to. Okay, so let's actually write a null alternative for this example. So a snack food company produces 454 gram bags of pretzels. The net weight varies slightly, because each bag's will be a little bit different. The company claims that the mean, or average, net weight is 454 grams. So first off, our null is pretty straightforward. They said the mean is 454 grams. That is our null in this case. So our null hypothesis would be that the average weight, so the mean weight of all the bags, is equal to their 454 grams. That's their claimed value. That'd be the null zero. So this would be your null zero in this case. Again, this is the null hypothesis. So the null hypothesis is that it's accurate. It's right. It is 454 grams. It is equal to 454 grams in this case. The alternative, so the alternative to the null, is going to be a statement that it's different. Well, they don't specify anything about being less than or greater than, so we'll say different. In this case, it'll just be that it's not equal to. So this one, the alternative, HA or H1, is going to be that the mean is not equal to their claim value. They said it's 454. We're going to say the alternative is not 454. Depending on motivations, you might do a test like this, and you might be like, I'm the government checking up on your label claims, and I might only be worried about if maybe it's less than. But if you're the boss of the company, you might actually want to be worried about maybe it being too much, because if you overfill your bags, you're losing money. So we'll just do not equal to this case. But a lot of times the alternative will be driven by the motivation of the person creating the hypothesis test. Am I worried about the bags being overfull because I'm losing money, or am I worried about the bags being underfull and shorting customers? So that probably be a driving motivation. Usually I'll try to write problems so that they motivate either less than or greater than or not equal to. This one, there's nothing telling me whether I'm doing less than or greater than, so not equal to make the most sense. Next one. College president claims that at least 85% of his university students graduate within 4 years. Sorry, I had a typo there. But graduate within 4 years. So this is at least. At least means that much or more, right? So in this case, we're actually thinking about more than 85% would be the other option, the option you just kind of think about. So we're looking at least, which is greater than or equal to. So here, the null, remember the null is always a statement of equality. I don't care that they're talking about at least and again about greater than. When I write the null is always a statement of equality. So here, they're showing 85%. So we're looking at not means now, we're looking at percentages. So we'd say the percentage, remember P is the percentage of the whole population, is equal to 0.85 or 85%. Null is always a statement of equality. If you write a null with a less or greater than, you're doing it wrong. Null is always equality. Did I hammer that enough times? I'm going to do it probably a few more times. Alternative in this case, the alternative here, the HA or H1, well now we'd say the p-value is, in this case, we're going to look that it's actually bigger than, right? Because they're saying at least 85, so 85 or more. So we're going to say the alternative is it actually is more. So sometimes your alternative will actually match up with your statement. So this claim they made was a greater than claim, and so that's going to match with the alternative. Versus the first claim, and the first one was a claim about equality. So the claim, the wordage of the claim can either match up with the null or the alternative, and either one's okay. That doesn't really matter. But you should always make sure that the inequality for the alternative is driven by the statement. So when they say, talk about at least here, then okay, we use that to figure out this is greater than. So P is greater than 0.85. 0.85 in each case, right? We're still with P in each case. Just the null is a statement of equality. The alternative is a statement of not equal. In this case, bigger. It's more than 85. Okay, so we're going to always state these two hypothesis, the null and the alternative, and then to do our test, we're going to assess, we'll collect some sample data and we'll assess how this works out. So that's kind of going to be the process, which I think is what the next page actually talks about. So I'll jump into that there. Okay. So the logic, the reasoning behind hypothesis testing. So after we figure out what our null and alternative hypotheses are, so we looked at the claim, figure out hypothesis, we got to decide, do we reject the null hypothesis and go with the alternative? The alternative is kind of our secondary option. So if we have enough information to reject the null, we'll go with the alternative. To do this, we'll collect sample data. So we're going to collect sample data, and then we're going to compare it with expectations based on the null. So if the equality is true, what would you expect? Would you expect a number close to that, right? We said that when you do means of a sample, they're usually close to the mean for the population. When you do proportion of a sample, it's usually close to the proportion of the population. So we'll take a sample, we'll collect data from the sample, and we'll compare that with the null. And we'll say, is it close to the null? If it's close to the null, then usually the null is pretty good. We'll just leave it be. If we're really far off the null, then we'll probably think about going with the alternative. So compare it with your expectations from the null, and if it's significantly high or low, we'll reject the null and support the alternative. So after we determine the null and alternative, we got to decide whether or not to reject the null in favor of the alternative. So we'll collect sample data, compare it with the null, and if it's really far different, then we'll reject the null and go with the alternative. So that's our process. State the hypothesis, collect sample data, compare it to the null, and then we'll decide whether or not to reject that null in favor of the alternative. Excuse me. Reject the null when the data we collect appears extreme compared to the null. So for example, if we claim 50% of Americans have health insurance, our null would state that the percentage is 50%. If you go and collect sample data, it says 46%. Now that's not 50%, but it's fairly close, right? And since this is just a sample, we expect a little bit of variation. There's millions of Americans. If we're just sampling 1,000 or even 100,000, that's still a drop, in the bucket compared to the millions of people there are. So we're not going to expect to get the exact 50% every time. We're going to expect to get close, but not exact. So 46%, we'll probably look at that and probably say, okay, that might be close enough. It's not too far from 50%. And we probably will just, say, okay, 50% seems okay, because that got close enough. But if we collect our sample data and get a value like 12%, 12% is really far away from 50%. It's not close at all. That's when we start to go, wait a second, this value I got from my sample does not match up with the 50% you're claiming. So I don't really think your 50% is accurate. I think it's probably much less than that, because when I sample, I only get like 12%. The more extreme the difference is, the more likely we are to say, that null doesn't make any sense. I'm going to go with the alternative, the other option, because that seems to make more sense. And so we're going to look at that, and we'll have ways to measure that. That's what we're going to get into, especially in the next couple of sections. We'll look at how to measure how different the value is, and then decide whether or not to reject the null. But that's the basic idea. The basic idea is you'll have a value you think that it might be equal to this. That's your null. And then you'll say, okay, I collected data and compare it with the null. The more extreme, the further away you are from that null, the more likely you are to reject the null and go with the alternative. So let's try an example. So the recommended daily intake of calcium for adults is 1,000 milligrams per day. So you should take 1,000 milligrams per day of calcium. You should get that much. Doctor theorizes that adults living probably get less than the recommended amount. Well, the null and alternative B's, we'll state those again, and then we'll do the next part after that. So we want the null and alternative hypothesis. He says that you should take 1,000 milligrams per day, but he thinks that people get less than that. So null, remember, is always equal. So that's the easy part, the null. We don't have to worry about less and greater than, null is always equal. Since this is your average intake of calcium, the null in this case would be for a mean, right? This is an average, not a percentage. This is a percent, this is a average amount. So the null would be that your average daily intake is 1,000 milligrams. That would be the null. The actual average intake is 1,000 milligrams. The alternative, again, would be the other option. Alternative, HA, is that the mean is not 1,000. In this case, he's theorizing that it might be less than, so we'd make our alternative less than. So we'd say it's less than 1,000 milligrams. So the idea is, if he goes out and collects sample data and shows with the sample data that it's actually really extreme, he might be able to show that the alternative is actually true, that it's less than. and have a reason to reject the equality. If he fails to show that, if his data is too close to 1,000, then he might not be able to prove his claim that it's less than. So that's why he said it this way. He's trying to see, can I test it with the test, with the hypothesis test, and verify that the alternative is actually more accurate, that the null is not really accurate. So what should the doctor do if he goes and collects his sample data and it is inconsistent with the null? So inconsistent with the null, that's another way of saying that it is extreme. So it's extreme and it supports the alternative. So this means the value he got actually is a lot less than 1,000. So maybe he only got like 900 or 800 milligrams, not 1,000 milligrams like he thought, the null says. In this case, he would reject the null, which is that it equals 1,000, and support the alternative. It's less than 1,000. So you got a result that's so small that he actually can stop and say, no, I don't think the null works. I think it's wrong. I think that it's not an average of 1,000. We're not getting 1,000 a day. People are getting less than 1,000 a day. And that's what he's doing when he gets extreme results. So these are values so much smaller. Now again, if he got something like 950, that probably wouldn't be extreme enough. It is less than 1,000, but it's only just of one sample, right? He's not able to look at everybody for all time. He's looking at just a sample. So he maybe picks a group of adults and measures calcium for a couple weeks. Well, that's just one sample from all the people taking calcium over all the years of their lives. So he can't conclusively say what the exact value is from just one sample. But he can compare his sample to the value he thinks it is, the null. And you can say, oh yeah, my value is so much smaller. My value leads me to believe that the equality, the null, doesn't make sense. I'm going to support the alternative. I'm going to say my claim makes sense based on this data. That it's less than. I showed it with statistical data. Okay. Now, when he does this test, and he comes back and says, okay, I'm supporting the alternative. I'm saying the null is false. He actually has the potential of making mistakes, right? Because he might have bad data. Maybe he didn't collect it very well, or maybe he just got a bad sample. That can happen, because even if you pick a random sample, you might just pick an unlucky random sample. So he has the potential for a couple types of errors. There are two main types of errors you can deal with. The first one is what we call a type 1 error. This is when you reject the null. So he says, the null is not good. I'm going to support my alternative. But it was true. That's a type 1 error. That's a big deal, right? I'm going to reject the null. You say the null is false, and I'm going to support my alternative. So now he's going to walk around and say, hey, everybody, I showed it with my data. I showed that it's actually that people take less calcium than they should. Well, if it turns out that people actually are eating as much calcium as they should, or taking as much calcium as they should, his claim's wrong, and he's going around and lying to people, and maybe they'll start taking too much calcium or something. Or they'll push to make changes in our diets and stuff they don't need to make. So in that case, he's making false claims. He's making a type 1 error. The other one is a type 2 error. So a type 1 error is saying the null is false, or false when it's actually true. A type 2 error is when you don't reject the null. So you say, oh, I'm not going to say the null is false, but it is false. So you should have rejected it. So this would be if he said, well, I didn't have enough evidence. I'm going to let the null stand. I'm going to say, okay, maybe people do take 1,000 milligrams per day, but they actually take way less. And he should have rejected it. He should have said, no, they take less. But he didn't. And so those are the two main types of errors. So you can either reject the null, you can say, null is not true, but it actually is true. Or you can fail to reject the null when it actually was false and you should have rejected it. Okay. So, for example, the mean score on a standard Higgs test is 100. Principal believes that his students score better than average. So his students are doing better. So the mean is 100. He wants to say that his students are better than average. Let's talk about the null and alternative. Well, null, as always, the null is that the mean really is. So the mean is 100. So his average for his students is 100. That would be his null statement. Yeah, my students actually just are average. His alternative for this, so his alternative statement would be that the mean is actually better than average, so his students are doing above average. They're greater than average, right? So his alternative would be yeah, my students are doing really good. So then he would go, he'd collect his data, and first off, he might, make a type 1 error. Well, type 1 error, what would that mean? Well, that would mean he rejected the null, but it was actually true. So type 1 error, he rejected the equals 100, the null, but it was true. So for him, this would mean he supported the alternative. He said my students are better than average, said his students are better than average, but they weren't. They were just average. And so now that might come back to bite them later when people look at the data and say, wait a second, you said your students were doing better than average, but they're not. They're just doing average. And so now he's made false claims about his students. And then people might take that and say, okay, well, you're lying about your students, and so we don't trust you anymore, and how he gets fired as a principal. So that's not a good thing. He doesn't want to make type 1 error, right? Because he's making claims and saying, my students are above average, and they're not. They're just regular average students. Type 2 error is the opposite, right? So type 2 error is he does not reject, I don't know why the T jumped over there, reject. So he's not rejecting the equals 100, but it's false. And so he should reject the equals because in that case it means that actually the greater than 100, the alternative, is true. So this would be the principal saying, oh, I went and collected the data, and it wasn't high enough above 100, so I didn't reject 100. So I said, yeah, I guess my students are just average. But he actually has above average students, and so he's not he's doing them a disservice because he should be out there saying, yeah, my students are doing great, they're above average. So, he said students weren't above average. He says, I don't have enough data to show they're above average, so they're not above average. But they were. So again, big deal. Maybe not quite as big a deal as the first one because he's not going to, probably lose his job with that. He's saying, oh, I couldn't show that they really were above average, but he should have been able to. They actually were, and he just wasn't able to show that. So those are two things. So this chart kind of shows the idea of what's going on. So you do your study, you collect your data, and you make two decisions. You either reject the null or you fail to reject, don't reject the null. If you don't reject the null, and the null was true, well, you did the right thing, right? Because the null was true and you didn't reject it, so you should have kept it. If you don't reject the null and it was false, oh, I didn't reject it, but it was actually false, I should have gone with the alternative, you made a type 2 error. If you reject the null and it was false, that's a correct decision. But if you reject the null and if it was true, I said, oh, the null's not true, but it actually was, you made a type 1 error. So those are the things that can happen. Now notice that you can't do both at the same time, right? Because you only get type 1 errors when you reject, you only get type 2 errors when you don't reject. Also, if it's true, you can only get type 1 errors if it's true, and you can only get type 2 errors if it's false. So that actually kind of leads to, there's a kind of dichotomy, duology, there's a split between these two. In fact, what happens is, if you decide to err on one side, say I'm gonna reject more often, so I don't make type 2 errors, so I'll just reject more stuff. What that leads to is you end up making more type 1 errors. I don't want to make as many type 1 errors, so I'm not going to reject as much. Because if I reject less, I'll make less type 1 errors. If you reject less, then you actually make more type 2 errors. So this makes it kind of hard for statisticians because they have to play this balancing act. What do I do? Because I got to worry about type 1 errors on one side and type 2 errors on the other side. So what we do is we deal with what we call the significance level, and we measure what's the probability of making a type 1 error. So the type 1 error, the probability of making a type 1 error is called the significance level, and we use the letter alpha. This is the Greek letter alpha. Alpha is the probability of a type 1 error. That's the probability of rejecting the null when it is true. So that's our alpha. We also have a letter for type 2 error. We won't use this nearly as much. It's not as important. So the probability of making a type 2 error is called beta. And beta is, again, the probability of making a type 2 error. So what we're going to do is we want to reduce both errors, but we can't. So instead, we're actually just going to reduce one in favor of the other. So to keep the significance level, to keep the probability of a type 1 error down, we're going to actually tend not to reject unless we're really sure. So if we don't reject until we're really sure, then we won't really reject unless we know, we won't reject the null when it's true, because most of the time we don't reject. So we're going to err on the side of caution. We're going to keep significance level low, keep the alpha low, and most of the time we'll fail to reject. Only sometimes we'll reject. So we're going to keep significance level low. That's the alpha. And it ensures that if we do reject, we are certain. We're pretty good. We're happy. We know that we should reject. So we're reasonably certain the null was false. However, if we don't reject, well, that's kind of our default situation. Most of the time we don't reject. That means that there's actually a good chance that the null might actually still be false. Like we collect the data and we said, oh, that wasn't extreme enough, so we're not going to reject the null. But there's actually a good chance that the null was actually false. Our data just didn't convince us enough, because most of the time we fail to reject. So this leads to us basically coming across. When we do a hypothesis, we only have two options. We can reject the null, which means our data was really extreme. We had extreme evidence, and it supports the alternative. It tells us go with the alternative. So we only do that with extreme evidence because we're kind of being cautious. But on the converse side, when we fail to reject the null, we do that for pretty much everything else. So if the evidence is not extreme, maybe there's evidence, it's just not that extreme, we still don't reject. And so that just tells us that there was not sufficient evidence for us because we're being really picky, which means that we didn't really prove that the null was true, because there's a good chance that the null might be false. So when we say this, we'll say if we have good enough evidence, we'll reject the null. If we don't have good enough evidence, we'll say fail. And fail is a good word for this, because the fail word means that we just didn't have quite extreme enough evidence. It doesn't mean that we actually had bad evidence and we definitely want to say the null is true. It just means that we didn't have good enough evidence to say that the null was false. So when we do our hypothesis test this way, we actually leads us to the fact that we can never actually prove the null. I always think of like the scientific method in science class. You can test a theory and you can prove it wrong, but you can't prove it true. It's kind of the same idea in this class. You can test a hypothesis and you can reject the null and say, oh, the null is crap, I proved it wrong. But you can't prove a null true. You can't say, oh yeah, my data can prove it true. Because the way we're setting up the test, the way we're setting this up, we're saying, oh, if I find extreme evidence, I will reject this thing. I will say the null is false and I'm going to support that alternative. If I don't find extreme enough evidence, I'm not going to reject the null. I'm just going to say, I couldn't disprove it. So you can reject the null, or you can fail to reject the null. If you fail to reject the null, that means it doesn't mean it's true. It just means you couldn't disprove it. So you can only support the alternative, not the null. So if you ever tell me, oh yeah, I supported the null, I'll tell you, no, you didn't, because that's not possible. You can't support the null. You can't say the null is true. You can say, I couldn't disprove it. I couldn't disprove this theory. I couldn't disprove this null hypothesis. Okay, let's look at an example for this. So a doctor claims the standard deviation of adult weights is 20 pounds. He collects some sample data and performs a hypothesis test. Let's look at the conclusions. So if his sample has, I guess maybe before we do this, let's just talk about what the null alternative would be. So the null, since he's looking at standard deviation and he has 20 pounds, we'd say the null would be that the standard deviation is equal to 20 pounds. And he says at least, right? So at least means greater than or equal to. So the alternative would be that it actually is bigger than. It's more than 20 pounds. Okay, so what if he comes back with a sample that's extreme? It's all the way up at 30 pounds. So this is extreme is an important word. Extreme is 30 pounds. It's nowhere close to 20. He said 20. He got 30. It's way above. In this case, he'd get an extreme result that's so far out there, he would reject the null. So he has good evidence because his value is so much higher than expected. It's so much bigger than 20 pounds we expected. We have reason to support the alternative. So we reject the null, we support the alternative, that the standard deviation is actually bigger than 20 pounds. He came up with evidence to show that. He did a study and said, hey, here's my evidence. It's way higher than 20. I don't think 20 is right. I have evidence to show it is more than 20. Now, that doesn't mean that the actual average for all people in the standard deviation for all the whole population is 30, because again, he just took a sample. So the sample value 30 is not going to represent the entire population. It only represents the sample. But it's so far from what we expected to get, because remember, you should expect your standard deviation to be close to the standard deviation for the whole group. His was so far off, it leads them to believe that our claim of 20 or equals 20 is not accurate. It's probably higher than 20. I don't know what it is, but it's most likely higher than 20. And that's what he's showing. He's showing that, I'm rejecting null. I have evidence to support that's actually more than 20. The sample standard deviation is more than 20. What if he did the test, though, and he came back with a very moderate, 23 pounds? It's still more than 20 pounds, right? But it's not that much more. It's fairly close, right? This is very moderate. It's close to 23. It's so close. In this case, he'd fail to reject. He'd say, oh, yeah, I can't show that this is different enough. 23 pounds is not far enough away from 20 pounds to make this extreme. So this is reasonable. It could happen. If the actual average standard deviation for the entire population is 20 pounds, my little sample could have a standard deviation of 23, and that's possible just because I picked a small sample. Right? I didn't pick the whole population. So in this case, he would fail to reject, which means he would not support the alternative. Now, would he support the null? No, he does not. He doesn't say the null is true. He says, I couldn't reject the null, so I can't support the alternative. I can't say it actually is more, so I failed to support my claim. Like, I can't show it actually is more. But he's not saying it is 20. It might not be 20. It might be more. It might be less. There's always the chance that it's something different than 20. He just didn't have enough evidence to reject the 20, so he's not going to start saying something else. This would be like someone, we talked about at the beginning of the section, the whole average human body temperature is 98.6. Someone goes out and does a study of a bunch of people, and they say, oh, my average I got was like 99 degrees. Well, that's not far enough away from 98.6. That's really close to 98.6. And so if they say, oh, I can't disprove it, they're not going to start using a new body temperature of 99 degrees when they couldn't disprove it. They're going to say, well, I'll just keep using 98.6 like everybody else does, because I didn't have enough evidence to reject it. It's the same idea. You don't have enough evidence. If your evidence isn't strong enough, you just fail to reject and just keep using the value that was claimed, the null. But we're not supporting the null. We're not proving it. If I have a theory in science that works, it seems to work, and I can't disprove it, I'm just going to keep using it until I find a way to disprove it. And that's the same idea here. So we're not supporting the alternative because he failed to reject. So we can't say it's more. We're not going to say it's equal to. We're going to say it's not more than. We can't prove that. We don't have enough evidence for it. Again, we're not going to say the null is true. We're just going to say, no, I don't have enough evidence to show that the null is false. Okay, so that's the basic idea. Now, to do these tests, to do a hypothesis test, you're going to have to calculate some values. And one of the main values you're going to calculate is your test statistic. So a test statistic is the result you get from your data. So I mentioned how you're going to take a sample set of data, and then you're going to use that to calculate, whether or not you should reject the null. And so to do that, we're going to calculate the test statistic. It's statistic from your data, from your sample data. And we'll use it as our basis for deciding whether or not to reject the null. This is typically going to be a z-score, a t-score, or a chi-squared score. We'll get to those in Unit 3, so don't worry about those yet. We've seen z-scores and t-scores already when we were doing the Chapter 7, doing the confidence intervals, and we'll be using the same z-scores and t-scores for proportions and means. We will do a little bit of standard deviations. That's where you'll see chi-squared show up a little bit later in Unit 3. So this formula here has these formulas. This chart has the formulas for the different test statistics. So if you're doing proportions, you'll get a z-score with this formula. If you're doing means, you'll get a t-score with this formula. And if you're doing standard deviations, you'll get a chi-square with this formula. Again, we won't see those until later, so you don't have to worry about too much. But those are the formulas for the different ones, for the different proportion, mean, and standard deviation. And again, z-scores are on the standard normal chart, t-scores are the student chart, and this one's called the chi-squared chart. But again, we won't see it for a while. Okay, so let's do this. We're actually going to use the z formula. So we're going to use the z formula from above to do this, to work with this information they have about a claim. So they said the claim is that the proportion of children who watch more than an hour of television a day is 0.35. So they say that this is the claim. More than 1 hour of television watched it's going to be actually less than 0.35. For a sample of 1642, so that's how many children they sampled, it was found that 540, so I had a bad number on here. I went and looked back at my old work and realized, why did I have that number? So I fixed it. So this is supposed to be 540. Found that 540 watched less than 1 hour children per day. And that should have been more. Wow, I had lots of typos on here. I don't know why I never caught those before. I caught one, then I didn't catch the other. So watch more than. Okay, so let's go back. Look what numbers they gave us. They gave us the proportion for the entire population that they're thinking about. They're thinking that the proportion is 0.35. That's what they want to think it is. So this is actually our null statement, right? Our null is that the proportion of people that watch, more than an hour is 0.35. The alternative for this one, would be that the proportion is less than 0.35. So it'd be less than 0.35. So if we can reject the null and support the alternative, we'd be able to prove their claim that, yeah, it actually is less than 35%. They watch more than an hour of television every day. We'll see what happens. But yeah, null would be equality. Alternative is less than. The other values they gave us a sample size, n. They gave us the number of successes. So this is the number of students that actually do watch, more than an hour of television per day. And I think that's all we need, right? We need p hat, right? So we need p hat. Remember, to find p hat, though, we just divide the number of successes by the number of sampled. So we can find p hat just by dividing. So I'm just going to do 540 divided by 1642. That's what that was, 540 or 1642. And that gives us 0.329. It's almost 33%, which is a little bit less than the 35% they said, right? So it is less, but we need to know, is it less enough? And that's why we're going to do some stuff like calculate the test statistic. So we're going to use this formula and calculate the test statistic from this. So to find this test statistic, or z-score, we're going to take the p hat, which we just found, so 0.329. We subtract p, which is this 0.35. That's the claimed value, the equal to the claimed value, so 0.35. We're going to divide by the square root of p, which is 0.35. Q, remember that Q is just the opposite. So if 35% do watch less than, then the 65% would be the 65% that don't. So that Q would be 0.65. 0.65 over n, which is our sample size, which is that 1642 again. And that's how we type that. That's how we get this. So this is the z-score calculation. I type in my calculator. Be careful when you type this in. You want to make sure the subtraction happens before division. So you can either use a parentheses on the top, or you can just type the top and get an answer and then do it. So I'm going to do it that way. 0.329 minus 0.35, so I get an answer. I did that first, so I get the subtraction first, and then divide by square root. 0.35 times 0.65 divided by 1642. You don't need any parentheses up there, so as long as you get the times in there, you're good. And I get negative 1.78. So the test statistic for this is negative 1.78. We'll use this test statistic as a way to determine if this is extreme enough. The more extreme the value is, the more extreme this z-score would be. So the further off that I get from that 0.35, the more extreme this will get. So 0.329 is maybe not super extreme. It is, it's 1.7. Remember, z-scores only go out to 3 and negative 3. So this is fairly extreme. Like, it's halfway there to negative 3. But yeah, the more extreme my data is, the further out I'm going to get. So if I am getting a z-score of negative 2 or negative 2.5 or negative 3, that's going to be really extreme. That's probably where I'm going to be most likely to reject. The more extreme it gets, the more likely I am to reject. So use the test statistic to determine whether or not to reject the null. And the test statistic always comes from the sample data. So we had to use that sample data we collected and get that test statistic. That's what we were doing. And you'll have different calculations for means and proportions. We'll do a lot more with these formulas in sections 8.2 and 8.3, where we are actually working on finding, doing the whole hypothesis test with proportions and means. Okay, there's two main ways to use the test statistic and to perform your test, you do your hypothesis test. We're going to cover both because they can both be used, and your homework will use both throughout for the next couple sections. So the first one is called the critical value approach. So the critical value approach takes the significance level. Remember we had our alpha significance level, the likelihood of making a type 1 error that we tried to keep really low. It'll use the significance level and it will determine critical values. It'll be kind of the cutoff points, basically. So critical values are your cutoff points. And then we'll compare our test statistic with those critical values, with those cutoff points. If your critical value is more extreme than the cutoff points, that's when you'll end up rejecting. So we'll have what we call the critical region or rejection region is values where if the test statistic is in those values, we'll reject the null. So values for the test statistic that reject the null. So these could be your extreme values. So this is when your test statistic from your sample data is more extreme than your critical values. The critical values are, again, how we figure out the critical region. So critical values are your values, that mark the critical region. And again, these come from your significance level. Okay, so based on this, we're going to reject the null if our test statistic is more extreme than our critical values. So reject the null when our test statistic is more extreme than critical values. If it's not more extreme, if it's less extreme, then we'll fail. So otherwise, we'll fail. Okay, so here's examples of what it might look like. It depends on whether you're doing a test with a not equal to, a less than, or greater than. If you're doing a not equal to, both small and big values could cause you to reject. So your critical values would be like the values right here. These values would be your critical values. And then they would mark off the region in the middle where that's pretty average normal stuff. It's not very extreme, and so you wouldn't reject. But the stuff that's way outside on the edges, that's where you would reject. So you would reject if your test statistic was in those ranges. So if it's more extreme, further out in those ranges, then we reject. If you're doing a less than tail, you're going to just have one critical value right here. And so we'll reject if we're in this region. So if your test statistic falls over here, you would reject. But if it was on this side, it's not extreme enough, then we wouldn't reject. And they have a right-tailed test, we'll have one critical value, but up here, so we'll look at big values. So notice here we're looking for small stuff so that we can reject when we're doing less than. We're looking for big stuff when we're doing greater than. Okay, so let's look at an example. Say you were doing a right-tailed test. So first off, let's just draw that. What would a right-tailed test look like? So right-tailed test has a region over here. This is your reject region because it's a right-tailed test. Whenever you do a right-tailed test, that's going to be a greater than tailed. So it's going to be a greater than. A right-tailed test is greater than, so we're looking for values in this region. Anything test statistic-wise that lies in this region will cause us to reject. Now, what is this region? Well, you have to use the critical value to figure that region out. So we'll look at the critical value. And so the critical value is 1.645. And see how it's a positive number because we're on the right tail? So this critical value tells us that 1.645 is the cutoff. Anything that's more extreme than 1.645 will cause us to reject. So what's the value? Well, the test statistic for this one, the test statistic is 1.75. And 1.75, since 0 is in the middle, right? Remember these guys, 0 is all in the middle. 1.75 is going to be over here in this region, 1.75. So 1.75 is more extreme, right? It's further away from 0. It's in the rejection region. In this case, because we're doing a right-tailed test, we'll say 1.75 is bigger than 1.645. Our test statistic is bigger than our critical value, and that's enough evidence for us to reject the null. So we reject the null. So when you're doing the test, you're looking, is the value I got from my sample data, is it so extreme that I reject the null? In this case, it's more than the critical value. It's beyond the cutoff. It's out in the rejection region. And so yes, we do reject the null. If I had only gotten like 1.5 for my test statistic, then I would have failed to reject it. I said, oh, that's not extreme enough. It has to be a value beyond 1.645. And again, this critical value, it's really good to be determined based on what our significance level is. So how much tolerance do we have for the type 1 errors? And that'll depend on the person when they're doing their tests. So some people will test at the 5% chance. I'm okay with a 5% chance of type 1 errors. Some people say, oh, I'm fine with like 10% chance of errors. And some people go like, I only want a 1% chance of errors. It just depends on the person. So that will change, and then that will change the critical value. And we'll see that as we go further on, later on. But that's the idea. You mark off your chart using your critical value. So again, the critical value is right here, critical value. And then you look at your test statistic, and if your test statistic is extreme enough, you reject. Again, if it had been over here, we would have failed to reject because this is the non-rejection region. We only reject if it's in the extreme region. Okay. How do you get those critical values? Well, the significance level gives us our critical values. So we use the significance level. Remember, that's the probability of making rejecting a true hypothesis. That's the type 1 error. So that to do this, what we'll do is we'll actually make it so that the area of the rejection regions is alpha, is the probability of making a false type 1 error. So the area in the rejection region should be alpha, which alpha, again, is the probability of a type 1 of a rejected a true null hypothesis. That's what significance alpha is. And we always try to keep alpha small, right? So we're going to usually have all small. That's why the alpha, the tails are going to be usually smaller pieces. Most of the middle is going to be the bigger piece. Because we only reject if we have really extreme values. So there's only probability of alpha that the test statistic will fall in the critical region, even if it was actually true. So the probability of the region here is going to always be area alpha. If you're doing two-tailed, you have to split the alpha between the two tails. So remember that. That's something important when you're doing two tails because you don't get to use alpha for all one tail. You have to split it up. So if you're doing the not equal to test, remember that's the not equal to test, you actually have to split the alpha between the two. If you're doing a left-tailed test, so less than tail, then alpha is going to be the region to the left. If you're doing a greater than, a right-tailed, then alpha is going to be the region to the right, the probability to the right. So notice that the z-scores, it's going to depend on if you're doing two-tailed, left-tailed, or right-tailed. Like if we're doing right-tailed, the z-score has alpha to the right. If you're doing a left-tailed, z-score has alpha to the left. If you're doing two-tailed, they both have alpha over 2 to the side. They have half of alpha on each side. So you're not going to have a whole alpha on one side, you have half of it on one side. Okay, let's actually do this. We're going to do critical values for a left-tailed test. The left-tailed test first, I'll do it in blue. We'll do a right-tailed test, a two-tailed test. All of this is going to be for the 5% significance level. So we have a 5% significance level. So first off, if I do a left-tailed test, so if I have a left-tailed test, I'll put it right here. Left-tailed test, my region is over here. I'm looking at, this is a left-tailed or a less than test. So my critical value is going to be right here, and my region here is going to be alpha, which in this case we said our alpha significance level is 5%. So this is going to be 0.05. So I need to find what z-score here would give me 0.05 to the left. Well, thankfully we have a way to do this with our calculators. Hopefully remember that we had that inverse norm. I'm doing inverse norm because we're going to be doing z-scores for this one. It even tells us right here we're doing it for proportion, so we're doing z-scores. It's inverse norm. We'd use inverse t if we were doing t-scores, but we're using inverse norm. 0.05 is the area to the left, so I'm going to put 0.05. Remember, these are standard normal scores, so they have 0 for the mean and 1 for the standard deviation. So we've seen this before, the area, the mean, and the standard deviation. So I would do that now. Tell me what the z-score is that has 0.05 to the left. So second distribution, inverse norm. 0.05 is my area to the left, 0 and 1, and I get negative 1.645. So this is negative 1.645. That's the z-score, and notice that these z-scores for the left-tailed test should typically be negatives, right? Because areas can be usually pretty small, so you're going to want a negative z-score that's over here to the edge and makes this area small. So that would be the z-score. This would be your critical value if you had a 5% significance level. So doing a 1% or a 10%, I'd have a different number because I'd have a different percentage here, so that would change and get a different value. So they depend on your area. The z-score depends on the significance level. How significant do you have to be? Let's do the next one. Let's do right-tailed test. So right-tailed test. Now instead of being on the left side, I'm doing it on the right side. So now I'm doing a greater than test, right-tailed. So I draw my region, and I have a right tail, so I'm going to have an area over here. Right tail, maybe make it a little bit bigger. It's going to look like that. So I'm looking for that z-score that has the area here to be 0.05, right, on that right tail. So 0.05 on the right. So to do that, I'm going to use the inverse norm again. But no, I want the z-score to be on the right side. I don't want a left side z-score. But thankfully, remember that this is a standard normal distribution, so we can just find the left value and turn it to a positive. So we can actually do inverse norm of 0.05 again, and 0 and 1, but then just make it positive. So I get the same value, I get the negative 1.645. But since I want the positive score, this one needs to be positive versus the one up here that was negative, I'm going to turn this one into a positive. So I don't even have to do the calculator way. Now, if you wanted to do this and get the positive, you could type it in as inverse norm of 0.95, because that would put 95% to the left. This is 0.95. And that way you would actually get 1.645, the positive version. So you could do it either way. You can do it with this way where you turn it into a positive, so make it positive. Or you can just do it with 0.95, because that's the other percentage over here to the left. So when you're doing right-tailed tests, you got to think about that. You always want a positive when you're doing a right-tailed test. So if you do it with 0.05, that's okay, just make it positive. But if you do it with 0.95, it's already got to be positive. So you just use the area to the left. Because again, this inverse norm always uses the area to the left. Okay, one more to do. So let's do the two-tailed. So I want to do a two-tailed test. So I'm going to have two tails now. I'm going to draw my region. So two-tailed. This one's the really important one because this one's the different one. So when I do my tail, I have a tail here and a tail here. Remember that I don't get to put 5% in both tails. I only have 5% total. So each of these tails only gets 2.5%. So this is 0.025, and this is 0.025, because I have to cut the 5% in half and split it between the two tails. So when I find my z-scores, my negative z and my positive z, these are going to be z-scores for this 0.025, not for 0.05. But I can still use that inverse norm. I'm going to go ahead and do it for 0.025, because yes, that will give me this value, but remember I can find the other one just by making it positive. 0, 1, now tell me the z-scores I need. So I'm going to do second distribution, inverse norm, 0.025, 0 and 1, and we get a little bit bigger number, right? Because now we split it up, we have to go further out to mark off this region. So we get negative 1.96 if you round it. And that's one of them. The other one would be the positive 1.96. So the critical values when you have a two-tailed, you have two of them, right? You have a negative and a positive. And those would be the critical values for that. So there you go. That's where critical values come from. All you really need is the significance level and what kind of test is it. You need to know, is it a left-tailed test where you're looking at the left region, a right-tailed test where you're looking at the right region, or a two-tailed test where you split it up so you have to use up a little bit in both ends. And it looks like that. So again, left tails are going to be negatives, right tails are going to be positives, and a two-tailed is going to have both. It's going to have both a negative and positive, but because we split up the number here, you see that the number changed. We had to go further out because you only have a little bit on both ends because we split it between the two. Okay, we're making progress. We're getting there. This is a long section, so we'll have to cover. We got about 4 more pages still. Okay. Now, this is just kind of running through the entire process now. So we talked about all the different steps. This is the process if you want to do a critical value approach hypothesis test. First off, again, you state the null and the alternative, and you get that from the claim, right? So you look at the claim, you figure out that, remember, that null is equal, and the alternative is going to be less than, greater than, or not equal to, right? So you make your statement. Next, you figure out the significance level. That's usually just given to you. So that's usually given. I shouldn't say usually. It's always given because they have to tell you. In real life, if you were like a statistician, if you've done this for years, you would try and determine your significance level based on the problem, the situation. Sometimes you need to lower the significance level. Sometimes you can have a little bit higher. But for us, we're not statisticians yet, so we'll just tell us what they want. So this will be given. And it's going to be small, right? It's going to be 1, 5, 10% would be probably the biggest you'll ever see. You won't see a significance level much bigger than 10% ever. Then we compute the test statistic. Remember, the test statistic comes from the data. So this is going to be a z-score or a t-score or the chi-squared score, and it's going to be based on your sample data. So you'll look at your sample data, and then you'll figure out what the test statistic is. Now, once you have your test statistic, you're going to go and you're going to figure out your critical values. Remember, critical values are from the confidence level, or sorry, significance level, and the tails of the test. That's how you get that part. So you look at it as a left-tailed, right-tailed, two-tailed, and then what's the significance level, and you'll build your critical values. And then you look and see, is the test statistic in the critical region? If it is, remember that's because it's extreme, then you reject. So is it extreme? That's what we're looking for. Is it extreme? And then we state the result. You either reject or fail to reject that null hypothesis. So that's the process. This is the process to doing a critical value approach. We'll do more of these in the next couple sections, but that's the basic idea. So let's run through that for this one problem we have down here. So the professor believes that less than 30% of his students, statistics students, fail the course. From a sample of college students, he determined the test statistic is negative 1.55. So he looked at the sample data and figured out his test statistic. Use the hypothesis at the 10% significance level, so that's our significance level, that's alpha, and assess his belief. So first off, we need to figure out what our null and alternative are, right? So our null hypothesis and our alternative hypothesis. Since he's looking at percentages, it's going to be p's. So we're going to say for the null, the percentage p is equal to 0.3 or 30%. Remember that null is always a statement of equality, so it actually is 30%. The alternative is going to be the other option. In this case, he's looking at less than, so we're looking for less than. So the alternative is the p actually is less than 0.30, less than 30%, like he said. So that'd be our null and alternative. Since this is a less than test, this is a left-tailed. So that's one thing you really want to pay attention to. Notice that the alternative hypothesis actually tells you if it's a left-tailed or right-tailed or two-tailed. So that's where you get that. Okay, so we're doing a test where we want the critical value of the z-score to mark off this region because that's our rejection region. This is where we reject. Remember, the rejection region always has the same area as your significance level. So this rejection region should be 10%. So this is 0.10. This is 10%. So we can use that now. We can figure out what our critical value is. So to find our critical value, we're going to do that inverse norm. We're doing percentages again, so we're doing inverse norm of 0.10, 0, and 1, because again, that's the area, the mean, and the standard deviation. And now tell us what the z-score is. So I'm going to do a second distribution inverse norm. 0.1, and 0, and 1. And tells us that the value we get is negative 1.28. So this is going to be 1.28. That is our critical value. So our critical value is negative 1.28. So if your value is more extreme than that, then we reject. So we're going to compare it. We're going to look at our test statistic compared to our critical value. So our test statistic is negative 1.55. You got that from the data. Our critical value is negative 1.28, so negative 1.28. Is this smaller? Yes, it is. It's smaller. It's more extreme because negative 1.55, I'm going further out in the negative direction. So because this is more extreme, so yes, the test statistic is more extreme. It's further out. If that happens, that's enough evidence for us to reject the null. So when our value is extreme, that's when we reject. We reject the null, which means we support the alternative. So in this case, since he said that since our alternative is that the proportion is less than 30%, we actually have evidence to say he's right. Our evidence points to the fact that yes, it is less than 30% of the students that fail. And so that this is the evidence that supports that. So we have evidence to show less than 30% fail. We don't know exactly what it is. We don't know what value he got, but we do know that he has enough evidence to show that less than 30% fail his course. He's collected the data and shown them. So that's what happens. So this is the idea. This is the process. One thing we kind of skipped over is how to get the test statistic. In the next couple of sections, we'll actually do that calculation a lot more and run and do these tests. So that's the idea. Now, I told you there's two different ways. Actually, I should have said three because there's three. But there's two that we're introducing in this section. So this is the first one. The second method is called the p-value approach. I will say that as time goes by and technology advances, I think that the p-value approach is becoming more prevalent. And from what I'm seeing, less and less people are using the critical value approach. I think we still have to cover it because it will show up in your homework and stuff and quizzes. And it's very easy to ask a question where you need to use the critical value approach to do part of the problem. So we're going to still cover critical value method. But the p-value approach, I think, is becoming more prevalent, is actually going to be more of the gold standard. Part of it, why, is because later I'm going to show you to do this with a calculator. The calculator actually will only do the p-value approach. So you can't do the critical value with the calculator. So that's something to notice for later. Okay, so let's look at the p-value approach. What's the difference? So on the critical value approach, we made these critical values, and then we checked to see if our test statistic was beyond those, and that's how we decide whether or not to fail, or to reject the null hypothesis. The p-value approach takes the test statistic and then figures out a probability based on that. That's why it's called p-value. It means probability value. So it takes the test statistic and figures out a probability, and then just compares the probability with their significance level. So you kind of skip the whole critical value part with this one. You take the test statistic, figure a probability, and then use the probability to determine with your significance level if we can reject or not. So the p-value approach, we calculate the probability of getting a result at least extreme as our test statistics. We're actually looking for the probability for our test statistic. And we say at least because you could get a number even more extreme than your test statistic, and that wouldn't make anything change our results. So we'll look at our test statistic, basically find the probability of the area for the test statistic and beyond, and then that's how we'll figure out the probability, because remember the areas under the curve are probabilities, and we'll compare that probability with their significance level. So the p-value is the probability of getting a value at least that extreme as the test statistic. The probability of getting that test statistic, or something even worse. And that's based on assuming the null is true, because if the null is true, then we can calculate this probability. You need to have some kind of reference point. More extreme values are less likely, right? Because if we say the null's in the middle, the value being way different from the null, the more different from the null is the less likely it is to happen by accident. So we'll say that if the p-value is small, that means our data is more extreme. So the smaller the p-value, the more extreme the data is, and then we're more likely to reject. So when p-values are small, you reject. So that's going to be the way we do this. So we decide whether or not to reject by comparing the p-value with the significance level. If the p-value is smaller than the null, or the significance level, then we reject the null, because the chances of getting such extreme result are slim. So if the p-value is less than the significance level, reject. If the p-value is bigger than the significance level, fail to reject. That's how this works. So you calculate your p-value. If it's small enough, you'll reject. If it's too big, if it's not small enough, you'll fail to reject. Your book has this fun little way to remember how this works. It says, if the p is low, the null must go. So if your p-value is small, the null must go. If it's low, it must go. If p is high, the null will fly. Remember, you can't prove the null, so you just got to let it fly. You just got to say, okay, I can't get rid of it. So that's the way to remember. I thought it was cheesy and cute, but hopefully it actually helps you think about it. Remember that the p is low, the null must go. We reject the null. We don't want it. If p is high, if the p-value is too high, the null will fly. We can't reject it. We failed. So it just got away. You always need to think about catching a bird. It got away. Okay. So let's look at an example. So p-value for hypothesis test is 0.064. So that's their p-value. Right? They went and they took the test statistic and they calculated the area under the curve. They found the p-value. The significance level is 0.05. Let's decide. Should we reject the null hypothesis, or should we, fail to reject? So we compare. We compare our p-value with our significance level. P-value in this case is 0.064. Significance level is 0.05. Be careful. Sometimes they'll give you one of these numbers or percent, and the other one will be decimal. Always make sure the same kind of number before you compare them. Don't compare a percent and this decimal. These are both decimal, so we're good. And we can see that 0.064 is actually a little bit bigger than 0.05, right? 0.0 and then 6, 0.0 and then 5. The 6 is a little bit bigger. Which means for us, since this is bigger than that, the p-value is too big, we fail to reject the null. P-value is too large. Now, one reason people like p-value is you can look at this real quick and say, okay, it fails at a 5% significance level, but maybe I can get away with like a 7% significance level. And a 7% significance level, you could actually still reject. So sometimes people will do a p-value because then they can kind of look at the different significance levels and they can decide which one works best for them, which I know is a little bit fudging your numbers. So that's why, again, people always want to look at the actual calculations and data before they believe too much about someone's statistics. That's something people do. They actually look at it and say, okay, if I get my p-value, I can compare it to a couple different significance levels and see how far I can get, how good is my evidence to reject the null. So this would reject at a 7% significance level, or 10% or something like that. And you're not going to see those as often. They're really less likely, but it would. But that's the nice thing about the p-value. You can see that really quickly. With the critical value method, that's not as easy to all of a sudden switch gears and say, what about a different significance level? P-value, it's easier to do. I think that's another reason why it's getting more popular. Okay, now how do you get those p-values? Let's talk about that a little bit. So to find the p-values, we're going to assume the null's true. So we're going to say the null's, the middle is average. We're going to say it's true. And then we're going to figure out the probability of getting our extreme value. So we're going to look at the probability of that test statistic being as extreme as it is. So we're actually going to find the percentage and the tails beyond the value. So we're going to look at the test statistic and find the percentage and the tails beyond the value. Remember, the percentage in your tails is the same thing as your area. It's the same thing as your probability. So if we use t sub 0 for our test statistic, so t sub 0 is our test statistic, then we got three different options. We got a two-tailed test, right? You have a two-tailed test where you're going to have the p-value is going to be the area left of the negative t sub 0 and right of the positive t sub 0. That's going to be your area. It's going to be combined. You're actually going to take those two areas and combine them all together. So this area plus this area gives you your whole p-value for a two-tailed test. If you have a left-tailed test, p-value is just the area left of this value. So for a left-tailed test, it's just going to be this area down here. That's your p-value. So just look at the one side. A right-tailed test, well, p-value is just the area to the right. So right-tailed test, p-value is just this area to the right of that value. So you'll take your test statistic. If you're doing two-tailed, you're both the positive and negative version. You'll find area in both tails, and then have to get the p-value. Really, in practice, you just find one tail and double it, because remember, these always match. So that's what I usually do. Is I just find the area in one tail and then double it, and that's my total. If you have one tail, you just find the area in the one tail, so beyond to the left or beyond to the right, which one, depending on which one you're doing. So for example, so everybody gives a test statistic of negative 2.5. So that's the test statistic they gave. They want the p-value for a left-tailed test. So if I make my test, I'm going to go like this. I'm going to say left-tailed test. This is going to be over here. So the negative 2.15 is this value right here. That's your test statistic. Because we're doing p-value method, we use the test statistic and we find this area. So it's a little bit backwards versus the critical value. The critical value, we kind of found the z-score based on the area. Here, we're going to find a area based on this test score. So we're looking for this region. This is going to be our p-value, whatever this area is. So to do this, we're going to go back and we're going to use that. These are z-scores. Normal CDF. Remember, that's the normal CDF is the formula on your calculator. They'll give you the area based on the t-score, or z-score. So I'll do negative 2.1. Oh, sorry. I'm doing that wrong. I need my lowest value. And this one would be like negative 10 to the 99th because you have your minimum value. And then your max value, which is negative 2.15, 0 and 1 for the mean and standard deviation. And so that's what we would type in our calculator to get that area. Second distribution, normal CDF. Whoops, I hit the wrong button. Second distribution, normal CDF. Okay, so the first number, lower bound, since this goes on forever, so for like left tail, we're not going to end. We'll use the negative 10 to the 99th. So that's just kind of going really small, as small as we can kind of get the calculator to go. Upper bound is going to be where we stop at negative 2.15, so negative 2.15 is where we stop. Mean and standard deviation should just be 0, 1, because this is a nice normal distribution. Enter, and we get the value. So there it is. It is, the p-value for this one is 0.0158 if you round it. Now, for this, the p-value, we would look at that and say, okay, well, what's the significance level? It's like if we had a 5% test, we would actually reject in this case, because 0.01 is less than 5% or less than 0.05. If this is a 1% test, we'd actually fail to reject. So that's, again, the nice thing about a p-value is you take your p-value now, this is your p-value, and then you can compare it with lots of different significance levels. So if you want to kind of find the one that works for you, you can do that a little bit. In real life, you usually have a reason why you use the significance level. So that's a little, skeezy to kind of pick one that works. But p-value, is a really nice thing because you can compare it with different significance levels. Okay. What if instead we did a problem where they gave us a t-score? Notice this one's a t-score now, not a z-score. The first one was a z-score of 1.71. And then we want to find the p-value for a two-tailed test. I'm just going to wonder, because I think I should actually have given myself. So then you're going, wait, shouldn't I have given myself some more information? Yeah, I forgot to tell you how many people are in this test. Can't really do a t-score test without a population. So let's say, just because I have to give you some number, let's say the degrees of freedom are 24. I should put that in the problem, but I forgot to. So that's why I have to give it to you. I was sitting there going, wait, you can't do t-scores with a sample size or degrees of freedom. So we'll say the degrees of freedom are 24, just so we have a number to work with. Okay, to do this, again, think about what we're doing. We're doing a distribution where we have two tails. So we have a left tail and a right tail. We know that the t-score is 1.71. That's the positive one, right? So the negative one's just going to be negative 1.71. And we're looking for the area on both. So each one of these is half the p-value, because we have to split it between the two. Well, the trick here is to find one, and then we can just double it and get both, right? So we'll just find the value of one area and then double it to get both. So in this case, I'm going to do a t-CDF, because that's how you find the area from a t-score. I'm going to do it with just one value, so I'll do from like 1.71 to 10 to the 99th, because I'm going to go from this value over to the right. So I'm going to just find this one side. And then I'll need, for that t-CDF, the lower bound, the upper bound, and the degrees of freedom, in this case, which would be 24. So that's what I'm going to put in there. So if I type my calculator, so I'm going to go in here, I'm going to type in second distribution, t-CDF. That's how you find the area from a t-score. 1.71 is the bottom, because I'm doing the right tail, so that's the bottom, and it goes on forever, so I'm going to do 10 to the 99th for the top, because it goes on forever, and then 24 for my degrees of freedom. So this would give me 0.05008. So this one is just slightly above 5%. So this one actually would, fail to reject on like a 5% level test. But if you had like a 10% level test, this would reject. So again, if you take this value, this is your p-value. Oh, I almost forgot. That was really bad. I shouldn't forget this. So I just talked about that. This is only one tail. So this isn't actually done yet, because in order to get the right test for this one, I have to double it. I can't believe I almost forgot that. Because so I double this, so it actually becomes 0.100 or 0.16. So this actually is like 10%. So it actually would fail even a 10% test. So this one's very unlikely. It's not very, very likely to do stuff. So this is the whole p-value. Again, you had to double because there's two tails. This was just one tail. We just found this area, so I had to double it. So that's the big thing you have to be careful about when you're doing these p-values. You have to pay attention. Are you doing a one-tailed test or a two-tailed test? Because if it's a one-tailed, you just find your p-value, you're done. You only have one tail to worry about. But when you're doing two-tailed, you find the area of one tail and then double it because you have two tails. It's just hard to find the two tails at once, so it's easier to find one tail and then double it to get your total p-value. So that's something you got to be really careful with these. Okay, now I said there's actually 3 different ways to test these hypotheses, and there's 3 ways. So the last couple pages, oh, I'm jumping ahead of the gun. Before I get that, let's finish with this section, with the steps. So just like before we had the steps for the test, this is the steps for the test if you're doing a p-value approach, right? A p-value test. So first off, just like last time, state the null alternative, right? And so we're going to start off with that. You have to figure out what those are. Again, those are from the claim. Just like if you're doing a critical value approach, it won't be any different for stating the null alternative. Next thing, again, determine the significance level. That is given. So it's not something you're really going to figure out. It's something you're just going to figure out from the question. Just look and see what they told you. We'll compute the test statistic. That, again, is the same. So all the first 3 steps are the same for each method. It doesn't matter, at all which method you're doing. You do the first 3 steps the same. Again, this is from your sample data. Then it changes, because now the next step for p-value is to actually figure out the p-value. That's where you're going to look at your test statistic and the number of tails. And that's how you're going to figure out your p-value, which is percentage. And then you actually look and see, is your p-value smaller than the significance level? If the p is small or low, reject. And then the last thing, you state the result. Did you reject or fail to reject that null hypothesis? Which one did you do? Is your p-value small enough? So that's the process for p-value method. Okay, so let's try one. So test statistic for a right-tailed test, so you go to right-tailed test, is z of 1.8. We're going to find the p-value and then decide whether at the 5% significance level we can reject or fail to reject. So if I look at what this looks like, so I have my region. I'm going to do a right-tailed test, so I've got my tail over here I'm looking at. Again, 1.8 is my cutoff point here. This is my test statistic for this one. Because when you're doing p-value, you put your test statistic here, and then this is your p-value. So we got to find that area. So we're going to use that, because this is a z-score, we're going to use norm CDF. My low value for norm CDF would be the 1.8. My high, or 0. The high value, I'm going to the right forever, is going to be 10 to the 99th, basically kind of going off to infinity. 0 and 1, because there's a nice standard normal distribution. Now give me the area I want. So I'm going to do second distribution, normal CDF. Start with 1.8, 1.80. Doesn't really matter if it's 0 or not. 10 to the 99th, because I can go off to infinity. 0 and 1, because it's a normal standard normal distribution. And that gives me 0.0359. So this gives you 0.0359. That is this area. So the p-value, the area here, is 0.0359. So then I'm going to take this p-value and I'm going to compare it with the significance level. So I want to compare 0.0359, the p-value, with the significance level, alpha, which is 5% or 0.05. So easy for people to look 5% and 0.03 and say, oh, they're different, or whatever. But remember, you want to make sure they're both decimals before you compare them. It's so easy to mess that up if you don't do that. Okay, but this one, either way, you still see that this value is smaller than 0.05. Remember, if the p-value is small, then we reject the null. So our p-value is small enough. We reject the null. We're good to go on that end. This tells us that they actually do have evidence to support the alternative. So we support the alternative because our number was so extreme, it was so far out there, that we do support the alternative. Okay, last step, last page. So I jumped the gun on this. So those 2 methods are kind of the big methods we introduced this section. We actually did introduce one more way of testing last section, which was the confidence intervals. So confidence intervals are a way to test hypothesis. And we saw before that if your value was within the range of the confidence interval, you could be happy, you could be content. And that's true. So a confidence interval contains the likely values for your parameter, so what we expect to have. So if the confidence interval does not expect to contain the claim value, then you can reject the null hypothesis. So if a confidence interval does not contain the claimed value, you reject the null hypothesis. Now the big thing is, when you're doing this, you have to make sure you construct your confidence interval the right way. And so that's what this chart is showing us. If you're doing a two-tailed test, your confidence level is going to actually be 1 minus alpha. That's how you do your test. If you're doing a left-tailed or right-tailed, a one-tailed test, then your confidence level is going to be 1 minus 2 alpha. Now, why is this? Well, think about what you're doing. So if you have your interval, and you're building your confidence interval, and you want to do a test with two tails, so alpha is in the two tails combined, right? So each of these is half of alpha. Then the middle part is going to be 1 minus alpha. That's going to be what's left because you take away an alpha between the two tails. But if you're doing a one-tailed test, so I only want one tail here, so I want all of alpha to be in this tail. Well, to build a confidence interval, you always have to have two ends. So the confidence interval is going to have also another alpha over here. So that's why in the middle you'd be taking away two alphas. So this would be for a one-tailed, and this would be for a two-tailed. So the difference is when you're doing a one-tailed hypothesis test, you only have one end, but when you're doing a confidence interval, you need to have two ends. So in order to make sure you have a whole alpha on the one side, you have to put another alpha over here. So you have to take away two alphas to get your confidence level. So like if say alpha is 5%, you'd have to put 5% here, 5% here. So you take away 10%, you'd only have 90% left in the middle. But if alpha is 5% and you're doing a two-tailed test, well, between the two ends you have 5% total, and so then the middle would be 95%. So it depends on which one you're doing. You really got to be careful about that when you're doing a confidence level test. So for example, let's do an example and you can see how it works in action. So a politician claims that at least 60% of his constituents want him to vote against an upcoming bill. If we want to test this claim at the 5% significance level, what confidence level should we use to construct a confidence level? In order to do this, we need to know is it a one-tailed or a two-tailed? Which one is it? Well, since he's saying claim is that at least, so greater than 68%, our null would be that the percentage is equal to 68%, so 0.68. The alternative would be that P is actually greater than 0.68. So this is a right-tailed. So we're going to make our test. We're going to put a right tail. The right tail should have 5%, right? Because we want the whole 5% to do our right-tailed test. But if I'm going to make this a confidence interval, so if I'm going to make a confidence interval, to have 5% on this end, I'm going to also have matching 5% on this end. So to do a confidence interval, I'm actually going to do a 90% confidence interval. So the confidence level would be 90%. Because I end up with 5% in both intervals. That's how I end up with the proper 5% here. If I match another 5% there and get my 90% in the middle, so I get a nice middle. If I'd only done 2.5%, if I'd done like a 95% here, I would end up with only 2.5 left between the two sides. So that's why I want to do 90%, so there's still 5% left, for each side to have 5%. Okay, so if our sample has a point estimate of 64%, so that's their point estimate, and a margin of error of 4.25%. So they did collected their sample data, and that's what they got. Would we reject the claim? So remember, to build the confidence interval, to get the confidence interval, what we do is we take the point estimate, which in this case would be p hat, and we add and subtract the margin of error, e. So this is the margin of error, this is the p hat, the point estimate. So I would take this point estimate, 64%, and I would subtract 4.25, and I would take that 64% and add 4.25%. That's how I'm going to get my confidence interval. 64 minus 4.25, that's going to be 59.75%. And this one's 64 add 4.25, so I get 68.25%. So that would be my confidence interval. So I'd look at this and say, based on this, do I have enough information? Can I reject? Well, because my claim value is 68%, and the claim value is in this range, I can't reject it. It's good enough, right? Because my range says anything between 59.75 and 68.25, anything in that range, I'll accept. It seems reasonable. So 68% is inside, so we fail to reject. We don't have enough evidence to reject it because it looks good enough to us. So we fail to reject because that 68% is inside. And that's how you do a test with a confidence interval. The hardest part with the confidence interval one is really coming up with the appropriate confidence level. So you have to be careful with that. Once you do that, you just build your confidence interval and then check and see is your number inside. 68%, which was the claim value, the P, is it inside that region. If it is inside, you fail to reject it. If it's outside, it's so extreme it doesn't fit in your interval, that's when you can reject it. Okay, I know that's a long set. Thankfully, the next couple of sections will actually be quite a bit shorter because this was introducing pretty much all the major ideas of hypothesis testing. So in the next couple of sections, we'll just take all these ideas and just actually do some problems with them, which in practice will go a lot faster. So thanks for sticking with me for that long video. I'll see you in the next one.